Well, MIT is a very different kind of institute. Instead of becoming the recipients of building industry culture, we can now change building industry by the kinds of experiments we're doing in school. MIT has a variety of departments that are so powerful that they have the potential of radicalizing what we do in design and in the architecture department. Even the way that we've structured our curriculum around workshops and other kinds of collaborations in a way foster and encourage this kind of cross-disciplinary platform. So we're situated perfectly for the kinds of things that only MIT can do.
The invention of human artifacts of any kind always consists of three elements: the geometry, the process, and the material that constitute that artifact. It's very clear that new materials engender new forms, and architectural design benefits from addressing, applying new materials in an informed way. The Emergent Materials Group and the Urban Metabolism Group share a central interest in materials for the built environment. Lately, we've been working a great deal in the area of foamed materials, especially foamed cements and concretes.
So typically a beam and bending is going to have the greatest amount of stresses on the top and bottom, so we can reduce the amount of material on the interior of a beam.
The work really tries to address that there's two main paradigms throughout almost every industry. The one paradigm is what can you design, what can you compute or analyze, and the other paradigm is what can you physically construct or what can you build. The work really tries to traverse all scale lengths. It tries to work from the nanoscale, which is traditionally where we see self-assembly in biological examples, chemical examples, and it tries to bridge that and say, can't we use this phenomenon of self-assembly as a new paradigm for building things at large scale? We work with any type of material, synthetic or natural materials, and really try to design specific geometries that have materials in mind. And when you design those two together, they can respond to energy. And the energy sources can be heat, shaking, gravity, pneumatics, electronics. So you can use any type of energy. And when you mix that with the geometry and material properties, then they can respond and they can change state. Primarily, it will first be applied in extreme environments, scenarios where it's difficult to build. The research and the practice is really about cross-disciplinary collaborations between designers, scientists, engineers, working on this phenomenon of self-assembly, discovering where we find it naturally, where we can use it synthetically, and trying to apply that at all different scale lengths.
The focus of our work, at least at this smaller scale, at the scale of, say, art installations or retail, we leverage CNC fabrication methods, but not as a way to exude their prowess necessarily, but more as a way to help us get at a particular formal agenda. An installation called totems, which in a way is a kind of proto-architecture, not quite architectural, not quite sculptural, but I think that it offers a kind of proposition to each of those disciplines. We do a lot of testing via 3D prints. A lot of the formal investigations for totems specifically happened in 3D prints. We did maybe 30 to 50 3D prints of the totems as a way to understand how the light and shadows were working and how best the anamorphic effects were working before we went to the large format wire cutter. In terms of collaborations, some of those happen here at MIT. Joel Lemire and I are developing an installation now, which is an anechoic chamber, and the anechoic chamber uses industrial felt both on its exterior and as a way to absorb sound on the interior.
I'm bringing a kind of disciplinary or formal or geometric interest on the one hand, also a certain set of specialized understandings of the behavior of these sheet materials on the other. So my architectural interests are really broad, but in terms of my current research preoccupation, it's about material geometry, specifically sheet shapes or sheet material geometries, how they bend, stretch, stack, fold. But obviously understanding sheet materials is really critical to architecture. It's a sort of a long-standing discourse on sheet materials in architecture, in part because it's so ubiquitous in conventional construction. So everything including plywood, sheet metal, steel, aluminum, plastics, all of these have to deal with the developable surface geometries, which is to say sheet shapes generally. And so expanding the total set of understandings about sheet shapes is a totally and kind of obviously worthwhile architectural undertaking. These installations attempt to jump from the scale of the paper model to, the scale of the architectural space at the very least.
Well, over the past 20 years, first as Office DA, now as NADA, we've identified 2 or 3 areas of focus. The first has been to look at materials and their behavior as a point of departure for many of the architectural experiments we do. The second area is to recognize that materials don't have an endless limit. Everything comes in modules, in sheets, in blocks, in bricks, and that without aggregation, there's no way of beginning to figure out how construction works in general. So the detail of bringing things together as a point of departure has been another central focus. So this has been a kind of point of revolution for a range of projects that we've researched and undertaken, some of which are at the scale of a piece of furniture, others that are at the scale of a building, and others that are really at the scale of urbanism.
One of the agendas of the studio is to create interactive architectures for public space through design and technology. And these projects can range in scale from the scale of the body, such as the Defensible Dress Project, which is a wearable architecture, which uses a microcontroller and shape memory alloys to defend your personal space, to very public scale infrastructural projects, such as our proposal for the Audi Urban Futures Initiative, where we're speculating on high-speed regional infrastructure and transformations in the city around issues of mobility for the year 2030. It seems now more and more necessary that our environments have to become smarter, more responsive, and more flexible. The way in which architecture is made needs to be completely rethought if we're to go beyond bricks and mortar to engage the challenges of the next century.
My work as an architect focuses on designing architecture and urban scale interventions that engage the emergent infrastructure of our time. We're interested in how design engages that mutability between energy and matter, when materials generate energy or store it, when materials are dynamic and change state, exchange heat, produce light, or communicate information. The challenge, I think, for the discipline of architecture today isn't in digital fabrication, it's in material fabrication, in thinking about what it means to be material today when we move fluidly between digital and physical realms, how we use materials and not waste them, and how we form materials and how we transport them. If we're going to change the building industry and regenerate an innovation-based manufacturing segment in the United States, then I think we need to do this from within practice, from working with the norms of the building industry, but not settling for those norms, instead innovating to both accept and transform those standard conditions.
I think we're pursuing several initiatives relating with computational material at several different areas. Dynamic interactivity is one with Hypersurface, and we're driving that forward. Imagining actively alloplastic environments, if you like. It's a demonstration of the power of computation come real time. Then in the robotic manufacturing work, we're looking for sort of power, information and material all coming together, but with control directly at the architect's workplace. So we're developing tools that allow architects within their native software like Rhino to pilot a powerful production machine like a KUKA robot, demonstrating, I think, what will be the future of manufacturing, which is sophisticated algorithms and modeling that link directly to sophisticated manufacturing machines and allow both new efficiencies but new versatilities, new formal complexities. I'm also frustrated by the slowness of the building industry to innovate materially. There's a fantastic amount of research in material science that's pent up and is just dying to come at a period where the sort of environmental concerns are becoming so enormous, and the challenge of building the developing world is so extraordinary that they're necessary. CAD/CAM meets material science like composites, I think, is going to breathe a whole new life into the architectural and building industries. So.